Good afternoon, physics class. Yeah, like old times. Old time. We're going to do seat changes this quarter. You guys want to switch it up?
Sort of.
Well, if you want to move, you can move. You like it? Who wants to move? Where you want? No. You're doing better up here. Yo, easy. I'm going to email your mother what you're doing in class time. Take your workout. Let's go. $10. What are you going to do with $10? Buy a soda? You can't even get lunch anymore for $10. All right, go down the bottom of page 16. No, 15. 15. We left a couple words off. Let's put those words on. By the way, you didn't really know anything. How was 6-8? If it was not good, tonight, that's why I sent that message. I changed the homework around, so you're not going to have another assignment tonight. So redo 6-8 if it wasn't good. You'll be better at it today. What?
I experienced some impulse on the weekend.
Proceed.
Oh, so I was in the shower and I had like this thing, like this container. I don't know what it was, but
Like a soap container?
no, like it was in the way. No, it was like a little metal thing. I don't know. So I like kicked it to the side, and then I was like, hold on. So I pushed it back, and I slowly pushed it back because it makes a loud noise when you move it. So then I was like, I just was playing around, and I was like, yo, that's impulse.
You were experimenting with impulse. That's right. Which one was more impulse, when you pushed it slowly or when you just hit it hard once? Probably.
It made like less noise. When I kick it, it makes a lot of noise.
During the kick or when it hits?
Both. Like when I kick it, it like goes on the ground, like makes noise while it's moving, and then it hits the wall. So it's like, boom.
All right, so see a lot of things in there. Actually, you got energy conservation, which we're doing next week. You got friction in there. You got all sorts of stuff. What metal box, by the way, sits in your shower?
It's like I don't know how to explain. It's like you could fill it up. I'll take a picture and I'll show you.
Like a flowering, like a water pot for.
Yeah. Like a pot.
Okay. Oh, I see. So if you want to like pour water over your head or something, or if you're having a tub or something like that.
I water my plants.
Oh, so it is a watering can.
Yeah.
All right. It's metal?
Yeah.
Huh. All right. Maybe it just needs to be cleaned. That's why I was in the shower. Yes.
What page are we on?
15, man. 15. Bottom of 15. All right, let's go here. Our new and useful concept here is actually what you just said there, impulse. I thought it said erase there. I guess not. We already looked this. Honestly, those notes. Yeah. Let's look here at 29. Maybe you guys know the answer then. Which situation delivers a greater impulse? A child pushing a wall for a minute or an adult pushing 10 times as hard against the wall for a second? What do you think? The child, yes. The impulse of the child, of course, is going to be F net times T. And the impulse of the adult is going to be F net times T. And in this particular case, maybe we'll say the child is pushing with a force F, but for a time, how long is the time?
We'll say 60.
Yeah, how about it's like 60 T? Whereas the adult is pushing with 10 times as hard, so 10F, and their time is just T. So clearly here, even without putting any numbers in there, who's going to be more? 60FT versus 10FT. So impulse is well, one of the ways really to make sense of impulse. One thing we said is the F net T, which is the time the force acts. So it's not just how hard you push, but how hard and for how long. And the result of impulse is ultimately this right here, change in momentum. If you provide more impulse, the object will change momentum more. All right, so let's go to the next page. All right, we only wrote one equation here. We wrote P equals mv. P equals mv more or less will guide you through all the standard momentum calculations. So momentum, to be a little more thorough, it's lowercase, it's minuscule p. Minuscule p. Yeah, this actually is not going to be homework tonight. Revisit W6H. Because either Friday or Monday, we'll see how it goes this week. Either Friday or Monday, you're going to have a quiz on impulse and momentum.
No.
Not Friday? Why not?
My birthday.
Oh. Then maybe Monday. We might naturally go to Monday anyway, since I'm pushing this homework back a day. So either way, 6/8 is important. So make sure if it wasn't good or if you just copied the solutions or whatever, do it better tonight. All right, momentum. We can tell. Well, first off, is it a vector or scalar? We talked about this last week, I believe.
It's a vector.
Good. It is a vector. Let me make sure we talked about this on Friday. Yeah, we did. We put the hats on everything. Good. All right. So, definition of momentum. You know, it's not easy to give anything other than just the equation-based definition. But one way to think about momentum, actually, and you playing sports, what does it mean to you if a player that you're going up against has a lot of momentum during a play? What would that mean to you? Like you're playing basketball, guy coming down the court your way, and somebody's like, that dude's got a lot of momentum.
It's going pretty fast.
All right. Is that it? Is it the only thing you would think?
Yeah.
Would you think anything different? Yeah.
It's hard to stop.
It's hard to stop him because he's not just fast. A lot of momentum would be big and fast.
Oh, yeah.
So massive and fast. So really, that's a nice kind of loose way to think about it. The difficulty stopping a moving object. That's why we saw that refrigerator Perry touchdown. Did he have a good amount of momentum? That's why it was very difficult to try to stop him. Now we have units over here. I'll erase them, but listen, you don't need to write out the words by now. You know the symbols by now. What's the unit for momentum? Unit.
Oh.
Look at the equation and it tells you. What's the unit for momentum? Emma? Yes. So this is a kilogram times meter per second. That's right. If you want to write out the words, you can, but honestly, there's no need. Just put the symbols. What's the other unit for momentum? Yeah? Yes, it is from the impulse equation. Newton multiply seconds. Okay, now, the easy box. The easy box probably would have helped you on that homework a little bit. Basically, coordinate your givens. The general equation is momentum equals mass times velocity. So if they ask you for the initial momentum, what do you think you have to do on the right side here?
Mass times VI.
Yeah. Mass times the initial velocity. If they ask you for the final momentum, mass times the final velocity. If they ask you for, which I believe I may have asked you, average momentum, it's mass times average velocity. And finally, if I ask you for change in momentum, it is m delta v, mass times the change in velocity. And so that one is pretty important. That's why I'm going to have you write it again right here. For a singular object, delta p equals m delta v. That one's pretty important. It comes up fairly frequently, and it's in the impulse equation. Okay, good. What do you know about the direction that momentum and velocity point? What do you know about that direction? Give me that phone. Stop playing.
I wasn't using it.
It was straight up and had your mother take $10 from you.
No.
Give me the phone.
Not paying attention.
It was not like,
Yeah, it's right there in your pocket.
Wait, it's not in my
Get up.
It's not it's
Up.
my backpack.
You lying.
No, look. It's right there.
Where?
Right there.
It's right where? Right where?
It's right there.
Give me that phone.
I was not using
Give me that phone. Marissa even saw you using it. Give me that phone.
Was I using it?
Yes. In that pocket. Good Lord.
Just didn't lose $10.
I thought you already won $10.
Nah, you might show off.
Listen, that's short money. You're working on long money here, man. That's what school is, long money.
Yeah.
Short money, that $10 ain't going to matter to you in a week. Your mother will feed you. Don't worry. All right. So how do they always point? Ika. Touch that. Ika. Yes, same direction. They have to be good. All right. We're gonna look at a couple of questions on here. Now, we're gonna jump down to 32. And be very clear about something this unit. The math is very easy. The equations, there's no squares, there's no halves, there's no multiply and divide. They're all P equals MV. J equals F net times T equals delta P. Like, these are very easy math problems. So you need not be so convinced that you're doing well when you put the numbers in and you get the answer. Don't pat yourself on the back for that. That doesn't matter. Setting up the givens. If you set them up well, that's the hard work this unit. You got it? So don't skimp and start pulling the calculator. Heck, half these calculations you can do in your head. The work here is the setup. All right, anyway, there's a couple just conceptual questions, and then we'll get into something like givens. So which has greater momentum, an earthworm crawling slowly or a honey badger at rest? Kohei, how you know? Good. So this one is the earthworm, and a honey badger at rest means the momentum of the honey badger is exactly 0. How difficult is it to stop something that's at rest? Well, not so difficult. Which object has greater inertia? Of course, why?
More mass.
Yes. The mass of the honey badger is greater than the mass of the earthworm. That's it. So I put this here because sometimes they'll give you a double question. They ask about inertia and momentum. You have to do each one separately. They're not the same thing. Can you describe a situation where the earthworm and the honey badger have the same non-zero momentum? Yes, you can. Stop it. Based on this equation, right? P equals mv. So think about it. Think about it. They both have momentum that's not 0, and it's the same. How is that possible?
Would the earthworm have to be moving faster than the badger?
Yes, that's all. So if you wanted to like play that font game we sometimes play, the momentum of the earthworm, it's a very small mass, whereas the momentum of the honey badger, it's a big mass. So for these two to come out the same, earthworm's got to have a big velocity, honey badger's got to have a little velocity. So it's possible. All right, now it's time for givens. Question 35. Nice, rich givens here. Let's go. You got to put some subscripts in there. All that jazz. And all that jazz. Get him over there in the margin. That didn't give you too much room. Thursday, huh? That's all right. Yeah, my mother-in-law's birthday party last night. You know what you wanted to do? Watch Top Gun Maverick. That's what we did. Come on, Henry, subscript that dog. Loosey goosey. All right, maybe you need a little reminder here what I mean by firming up these givens. Notice there are two masses up here, right? You're going to have to indicate which is which. Maybe mass of the ball is 50 kilograms and mass of the cannon is 1,000 kilograms. You're going to need to keep track of which is which. Now, there's a speed up here, obviously. I'm going to put a V. I'm going to leave some space, though, and then write 3 meters per second. We need to somehow define that speed. So when it comes to impulse, the question finally here, what is the impulse delivered to the cannon? So that's our question mark. You could say Newton seconds. When it comes to impulse, you have to think about what is actually happening. So you have a cannon. Maybe this could be our cannon. You have a cannon. I'll draw the board in case people are out. Here's your cannon. Inside the cannon, there is a cannonball. Now, at some point, you ignite this thing, it goes boom, and there's an explosion here, and the ball goes out of the cannon. Does the cannon stay put? No, the cannon actually, it recoils, they call it. And we'll look at some videos of that when we're doing momentum. So the cannon backs up, and the ball goes forward. Just from your common sense, do they move at the same speed as each other? That's the whole point of a cannon, right? You don't want the cannon to move very much, but you want the ball to go far. So they're not going to go at the same speed. You want your cannon to stay where it is. You want the ball to go and hit the target. All right. The impulse is happening during this explosive phase right here. So when they say the cannon recoils with a speed of 3 meters per second, what V is that?
Yeah.
That's a VF. You see that? That's a VF. That's a VF. And it's not just any old VF. That's a VF of the cannon. That's right. Do we know another V for the cannon? Like, do we know the VI for the cannon? That might be helpful. 0. So it's important to stop and think, wait a minute, what's actually happening here that's causing this impulse? All right, so once these givens are set up, it's time to pick an equation. Now, you remember from impulse, we had a bunch of equations. J, F net T, delta P, M delta V, MAT, all this different stuff. Which one makes sense with the givens? Swain? Okay. Now, might you jump that actually to what we know delta P equals? Now, they're asking about the cannon. So might you jump? You can say delta P. You're not wrong. But we also practiced what delta P is equal to, and it may be worth jumping right into that. Yeah? Christy? What do you think? Now, if you say just delta P, were you going to figure out the momentum initially and then finally and subtract the two? You could do that. You could also jump to, so you can do it either way. You can do it like this, or you could jump to this. Either one is fine. They both do the same thing. The only thing I want to make sure of here is, what are you putting in for that delta P or that delta V? Because numbers here are very easy to use. What are you putting, like, substitute this one right here. Substitute this one. What's it going to say? Emma? 1,000 times? Well, delta anything is always final minus initial. So 3 minus 0, right? It's going to be 3. Now, do we need a unit over here? Thomas? Why? There's a cleaner way to say it. Young Yak?
The difference between the change of V and VI. So you have to put the.
Oh, yeah, all right. Now, what were you going to say?
I was gonna say there's no given for change.
Right. You see that delta V is not written over here. And I know it's a little overkill, but this is the way they do it. Because it's not written over there, you got to put the unit over here. Swain, if you do this one, you're going to have to also put a unit in for that delta P. All right? But you see the math, 1,000 times 3, you don't even need a calculator. But the setup is where the work is done. All right. If the mass were doubled, velocity stays the same. What happens to momentum? It's pretty easy. P becomes, mass is doubled, that's a 2. Velocity stays the same, that's a 1. 2 becomes double. That easy. That easy. You can do it, Emery. We're almost there. I know, I'm sorry. All right, set up the givens for 37. It's another one. Nice problem. I'll put this on the quiz. Are people starting to get sick again? Yeah? That's why you better not be sick.
These are the next presentation.
No. There's, I'll put actually a big note up here. Custodian. Hopefully you see it tonight. And you'll be able to blow your nose with the world's best tissue again. You just have to hold it till then. Celia, hit us those givens. All right, you could jump at the 1500 if you prefer. Keep going. Is it the what? I don't know. Read the whole question, see what you think. What do you guys think? Stonehead? He says VI. Well, is that happening before or after the hit? That 12? So it's a VI, right? The VI here. So this is the car. The car is 12 meters per second. Now, would anybody do anything? Would anybody write anything extra? Yeah?
I made it positive.
Made what positive?
East.
Good. Because you're coming over here, you read. East! Come call that positive, because that's going to matter. That's going to matter. Robert, next given.
The F of the car is -2 meters.
Yeah, you don't have that negative there, it's not going to come out correct. Finally,
MJ car equals question mark newtons per second.
Newton's times second. Be careful. Right? F net times T. Per means divide. You could even just say Newton seconds. All right? Now, you see where you can go wrong in this problem? Which equation? Which equation are you going to use here? Let's see. Who haven't we bothered yet? We bothered pretty much everybody. Ray, what equation? Okay. Now, here's the one. Here's what I'm concerned about. What do you put in there for that delta V? Or what would you have put in there for the delta V had we not talked about it? It is. So what would you put here?
-2 -4.
And what would that give you? Negative what? Yeah. Now, I'm going to put this question on the quiz. And you know what people are going to put, right? Can you imagine it now? 4 answer choices. Choice 1 will be m times, what could I do here? What do you think I'd put for the delta V? 10. Choice 2 might be m times -10. Maybe you're like, oh yeah, I got to do this one minus this one. Choice 3 will be +14. And choice 4, -14. So all 4 possible ways you could do this, 3 of which are wrong, will be sitting there waiting on you. So you got to have your givens set up right. You know, it's not like I'm going to put other crazy answers. That's, by the way, tests that are written properly, the other answer choices are ones that you would get if you mess something up. They're not random numbers. All right? So that's why you got to be sharp with the givens. If you don't define this positive, you may not put that negative on the 2, and there it goes. You'll think 2 minus 12, you put a 10 in there, you won't get the right answer. This, by the way, comes out to negative 21,000 about. So what is that? The actual quiz won't say positive and negative. It'll say what?
21,000 meters per second west.
Good. Newton times second. West. That's right. Put that up there. This would say what? So the 4 answer choices, one will be east, one will be west, one will be east, one will be west. When you see that question there, don't say I didn't tell you anything. Don't say I didn't give you anything. Good. All right. How about this one here? This little piece right here. Well, there's a question, but let's go up here. You guys know Newton's third law. Newton's third law. What does it say? What's Newton's third law say? Come on, we spent a little time on it. Emery?
Every action has a reaction.
Good. And if we were to write that in terms of force, if I said the force of 1 on 2, what would that be equal to?
2. Wait, what?
What?
Wait, what'd you say?
Who? This.
1 on 2?
2?
No, 1 on 2. Wait, what?
Yeah? Come on, man. Do it. Do it.
I don't know.
It's always the same syntax. Syntax is the way you say things. The force of 1 on 2 must be equal to... Oh, come on, man.
1 on 2.
You said equal and opposite. So the opposite is negative.
2.
Force of
Oh, it's not a number.
2 on 1. No kidding, it's not a number. There's no number, there's a formula.
Oh, you said number.
What? I said, what does it give you?
Yeah, what is it equal to?
Yeah, I didn't say anything about number.
It's the same thing.
Not in this case. All right. Now, is this okay, though? Does this make sense? When you pushed on the table, let's say you pushed on it for 1 second. How long did the table push on you? Hey, can you cheat and like push it a little longer than it pushes you? Like, oh, I'm a sneaky. When it's not looking, I'll put a little extra in there and it won't get me back. It's impossible, which means the times that these things push each other are exactly the same. Which means if we multiply the left by the time it acts and the right by the time it acts, that's the same exact thing because they're the same times. Well, what's F times T? That's a new formula we've been using. Impulse. So the impulse of 1 on 2 must be equal and opposite to the impulse 2 on 1. That is another version of Newton's third law, equal and opposite impulses. Which helps you answer this question. If the car felt 21,000 Newton seconds west, the moose experienced what impulse? 21,000 Newton seconds east. Of course. There's one more version of Newton's third law, by the way, from the impulse equation. Anybody see what it would be? Look at the equation in your reference table. It's right there in front of you, young Yak. It's on the table. There's a singular thing there.
Are you asking me?
Yes,
I
you.
don't know what was the question.
I know.
You got me in the moment. I like actually.
The moment, huh? You know, when you start stringing a lot of those moments together, it ain't a moment anymore. All right. Here, another version of Newton's third law. So we have forces are equal and opposite. We have impulses are equal and opposite. There's even one more.
J equals F net. D. What do you mean?
Bill, do you know?
I don't know. Does it involve P?
Yes.
So P before is P after?
Actually, that's another version of this, but simpler. Just pull it straight off the equation. Yes?
P equals MV.
The change in momentum of object 1 is going to be equal and opposite to the change in momentum of object 2. That's actually another version of Newton's third law. That one will lead us to what you said there, P before equals P after. Okay, good.
Wait, I got a question.
What?
You know how like when you're like hanging on like a pole or something, like you like swing forward, you swing back.
Yes.
That's like building momentum, yeah.
Well, if you're gaining speed, you do build
You have to
momentum.
Move a little forward like this, you move back and kick back and keep moving, and you like
Yes.
when you go flying.
Yes. You are building momentum as you do that. That's right. That's right. You could equally say you're building speed. Usually in those scenarios, it doesn't particularly matter that your momentum is gaining. Bless you. You're right there? Oh, yeah, it really would. There is some back there, though. There, just don't use the edges of them. They're all the way over in that first lane. Keep going. There it is. All right. So that's just as well. You could use that. Behind you is the paper towel. You're really building speed in those because you become a projectile. You've seen in those shows like American Ninja Warrior and all that. Right. So they're swinging on a trapeze and they let go and then they actually are a projectile. So they need a greater initial velocity. So yes, they're building momentum, but really it doesn't matter if they're light or heavy, as long as they get that speed going. Yes. All right. These you could do. These are regular math. I wanted to show you one thing on this one, by the way. This one gave you an acceleration, gave you a mass, and it gave you a time of contact. So that should just remind you of this is from F net T, but MA times T. But I want to point out something else here because I'll give you a question kind of like this on the assessment as well. The acceleration here looks like a very big number, doesn't it? That's 18,000 meters per second squared. That is not a strange thing. Objects can experience very big accelerations just over very short time intervals right here. So in sports, any collision, be it a bat with a ball, a racket with a ball, a player with a player, even when you're catching something, they're very quick, meaning the time is very short and the accelerations are very high. And that's why people get hurt. And that's why things break. And that's why even, rackets and baseball bats and those things break as well. They experience a very large acceleration, but it's over a very short amount of time. So if you get an answer of 1,000, 2,000, 5,000 meters per second squared, don't get upset like this is impossible. If you're throwing a baseball and you get an answer of 5,000 meters per second velocity, you should worry. That doesn't seem reasonable. But 5,000 meters per second squared, maybe an acceleration of a ball hit off a bat, not as crazy. Not as crazy. Not Kohei's bat, but somebody. All right, come on down to these graphs. I know you didn't fill them in. You could just make them all direct. It doesn't matter. I just want to make sure we understand the slope. Ask you, Kohei, do you play baseball? Maybe it is off your bat. Are you a power hitter?
Maybe.
All right. Working on it for this season?
Actually, I have a workout tonight.
Wow.
Yeah. I'm good.
What do they have you do?
Like eating.
All right. That'll be fun. You might be tired, but. All right. Over here, we have 5 slopes. What I want from you is a quick answer. That means don't think about it yet. Quick answer. Slope is rise over run, delta y over delta x. So with the quickness. Got it? First one, Robert. Break the ice. What's the quick answer to this one? You're thinking too much. Marissa?
Pass.
No, you thought. I don't want you to think. The quick answer. P over V. Really delta P over delta V. But P over... That's what I mean by the quick answer. Truly, you should do this first. Stop trying to be so smart. In June, you're not going to remember all these graphs. But quick answer you can remember. Quick answer is easy. You don't have to know anything. So let's go. Next one. Kohei. Quick answer. Good. J over T. Young Yap. This one.
Change of P over J.
All right. PJs. Next one. Okay, so you're all getting the feel for this, right? Just read what the axes say. Delta P over delta V. If you do this, you set yourself up to get these right. Then, now you go use your brain, figure it out. So Marissa, you're right. If you go look this up, this comes out to mass. Yes. If you go look up J over T, it comes out to F net. If you look up delta P over J, it comes out to. Sounds a little tricky. It's a good one though. They sometimes slide one of these on the regents just to see if people get rattled by it.
Is that 1?
It's 1. Because they're equal to each other, it's 1. Right. This is equal to the number 1. That means this graph will always be just a slope of 1. There's no multiple versions on this graph. Delta P over F net. All right, Robert, take it away.
Wouldn't this be 1? Well,
No. No.
Impulse.
No.
I don't know.
Yes, you do. Look at your equation. J equals F net T equals delta P. Pick a piece here. Delta P over F net, right? So we'll look at this equation.
T.
T, you see? That's
Could
it.
also be impulse.
No. Because it's not delta P, it's delta P versus F net. So it's gotta be over F net. So you would have to divide impulse by F net also. And the last one, delta P, delta V, gives you your mass again. All right, there's 2 of them down here for area. Same game. Now we're doing area under the graph. Don't get crazy. Give the quick answer first. Heirloom. What? Nope. Area. There's no division in area. What is it? Yes, M times delta V. And then, Chrissy, what about the next one? Okay, and then you can see what these are equal to. M times delta V was this piece of, you could say delta P, or what else could it be?
Impulse.
Impulse, it could be J. In this one, F net T, typically you say J, but it also could be delta P. They're the same thing. That, by the way, is one of those questions that messes people up. They put that in the region sometimes too. They say, well, the change in momentum of the cart was 2,000 kilogram meters per second. What impulse did it receive? And people are like, I need to calculate. There's nothing to calculate. J equals delta P. Done. Why are you guys packing up so early? We still got a minute.
May I get my phone back?
There's tissue back there. You could use a little toilet paper. It's not even used.
May I get my phone back?
Why are you so impatient, man? I'm not throwing your phone. Come get this thing. Actually, here's what I want you to do. Come here. Come here. Oh, I want it to open right here. I want to see what app is there. Go ahead. Man, that's not even chess.
No,
You want text
no.
message?
It's a game pigeon. It's a game pigeon chess. It's on text message.
Game pigeon. Phil, do you play that game pigeon chess? Is it fun?